So in this lecture, we'll have a look at the definition of the conditional expectation when we're dealing with continuous random variables. So you should certainly study the definition of conditional expectations for the case of discrete random variables before doing the continuous case. It's way simpler to understand. And we will simply do the continuous case by deriving results analogous to what we have in the discrete case. So starting point x and y are continuous random variables. We are given some partial information, that is, we know the outcome of one of the random variables. We know that x came out to be lowercase x, but we do not know the outcome of the y random variable. With no partial information about x, all information about the y random variable is captured in its PDF. So this is the probability density function of y with no partial information. We can also call it the unconditional PDF. If I happen to know that x came out to be equal to lowercase x, then this will typically change the PDF of y. This will change to the conditional PDF, y given x, which we write like this, where this conditional PDF is defined as the joint PDF divided by the marginal PDF of x. If we change the probability density function of y, we will also change its expected value. The expected value will go from its unconditional value, which is the integral minus infinity, infinity, y times the marginal of y. With the partial information, if I know that x is equal to x, this expected value will then change to minus infinity to infinity, and now I have to use the conditional PDF. Y times fy given x, y given x, dy. We call this the conditional expectation of y given that x is equal to lowercase x. So what's happening is basically something like this. Here is my y-axis. Maybe this is my PDF unconditionally. I don't know anything about x. This will then be my unconditional expected value of y. Suppose that, for example, that x and y are positively correlated, and we know that x happens to take a untypically large value compared to its expected value. Well, then that will change the PDF of y as well. So it may become something like this. The conditional density of y given x. And that will then also change its expected value to the conditional expected value of y given x. If we look at the expected value of y conditionally on x being equal to lowercase x, for a given real number, lowercase x, the conditional expectation will become a real number. But in general, it will depend on what value we use for lowercase x. So this thing here will be a function of x, which we can denote by g of x. We then define expected value of y conditional on x without the equality sign after the x random variable, simply as g of x. That is, this thing now becomes a random variable. Here is an example that will illustrate this. I start with two continuous random variables and a joint PDF f of x, y. It's a simple one, x plus y, where the range of x and the range of y is the interval 0 to 1. If I have partial information, I observe the specific outcome of x. So lowercase x is an arbitrary real number in the interval 0 to 1 with infinite precision. By integrating away x from the joint PDF, we find that the marginal PDF of y is given by this information. This function has complete information about the random variable y, but it's based on knowing nothing about x. If, on the other hand, I know the outcome of the random variable x, then the relevant distribution is the conditional density, which is the joint divided by the marginal of x. This is the joint, this is the marginal of x. Note specifically that the conditional density will depend on y as well as on this particular value of x that we have observed. So this is the unconditional expectation of y. I integrate y from 0 to 1, y times the marginal of y. This integral comes out to be 7 over 12. If I know that x has taken a specific value lowercase x, the interesting expectation is then the expected value of y conditionally on this information, which is the integral over y times, and now instead we use the conditional density. The one we found up here, that should go in there. If you perform this integral, the expected value comes out to be this. That will be a function of x only, and it depends on the particular value that we were given for the random variable x. So this is my g of x function that we identified up here. This is my g of x, the conditional expectation given a specific value of lowercase x. Once I have a function of x, I can create a new random variable by feeding my random variable into the g function. This is this conditional expectation. So this conditional expectation is this random variable. It's not hard to see that g of x is a decreasing function of x when x is between 0 and 1. G of 0, which is the expected value of y if we happen to observe that x is equal to 0, that's 2/3. While g of 1, the expected value of y if we observe x equal to 1, is 5 over 9. Since g is strictly decreasing, the range of this random variable z must be between 5/9 and 2/3. There are techniques for figuring out the probability density function of z when it's given as a function of x and I know the PDF of x. I won't do that in this particular lecture. If you know how to do it, then you will be able to conclude that z is a random variable with a PDF given by this formula with the range going from 5 over 9 to 2 over 3.